Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about convex combination algorithm. So, today also we will be continuing that. So, in this convex combination algorithm, if you recall, we want to find new point xn plus 1 given the current point xn plus alpha n times this dn. Okay. So, currently we want to determine what is this descent direction dn here. Okay. So, for that uh, we want to determine this new point y such that this direction from xn to ya gives the largest reduction in the function value. Okay. Okay. Now, since we are interested in the reduction of this function zx here, so and we are moving in this direction y minus xn. So, the slope of minus zxn in this direction y minus xn will be given by this dot product here. Okay. So, if you recall, this is the unit vector in this direction y minus xn. Okay. So, that is why we are taking the dot product of this unit vector with gradient zxn. Okay. So, the drop in the objective function in the direction y minus xn is obtained by multiplying the above slope with the distance from xn to y, that is this norm of y minus xn. Okay. So, this overall is actually telling us what is the slope in this direction y minus xn. Okay. And this is a unit vector here. Okay. If you want to actually know how much drop happens in the objective function value when we go from xn to y, so then we also need to multiply it with the distance that we actually travel from xn to y, which is given by this norm here. Okay. So, therefore, if you multiply it with this here, so we will be getting this minus gradient z xn dot y minus xn transpose. Okay. So, this is actually telling how much drop in the objective function value happens if you move along this direction y minus xn. Okay. So, this is not very difficult to understand. For example, if the objective function value is decreasing in this direction, this is the minus gradient of z here. Okay, obtained at point xn. So, suppose you are currently at xn here. Okay, this point, but actually we are moving in this direction, this y minus xn. So, therefore, since we are going in this direction, we need to determine the projection of that here. Okay. So, that is why we are taking the dot product of this with this here. So, we need to maximize minus gradient z xn dot product with y minus xn transpose. Okay. But we need to make sure that this new point y is in the feasible region. Okay. So, if you remember, why we had not decided to just simply take the direction which was opposite to the descent direction, because it can happen that we may not be able to move that far in that direction, so that we see maximal drop in the objective function value, because we can soon encounter infeasible points. Okay. So, therefore, since we have the constraints in the overall optimization problem, linear constraints, so we want to make sure that this new point y that we find is in fact in the feasible region. So, equivalently we can minimize this gradient of z dot product with y minus xn transpose in terms of y, while ensuring that y is in the feasible region. Okay. So, previously we were trying to maximize minus of this quantity here. So now we have equivalently written it as minimization of this, okay, while ensuring that this point y is still in the feasible region. Okay. So we can write it in this form here. So this we have now writing it in component wise form. So this is equal to this summation over all the component I gradient of z at xn multiplied by yi minus xin, okay, subject to these constraints here, okay, that this variable y is satisfying the constraint that we have, okay. So this is just ensuring that y is in the feasible region, okay. So these are the original constraint that we had, we have just replaced xi with yi here. Now note that when we are trying to determine y, xn is already known because we are at the nth iteration. So therefore this gradient of this function at xn is also a constant because xn is constant, and therefore the gradient of this function with respect to xn can be dropped from the objective function, okay, because this is also constant and this is also constant because xn is known. If xn is known, the gradient of the function at that point can also be determined, okay. So that is why when we are doing this overall dot product, there will be one term which will be involving this gradient of z xn with xn transpose. So that is a constant, so that can be ignored, because if you remember we had discussed this result that suppose if you are minimizing an optimization problem with the objective function, suppose say z plus some constant, so then the optimal solution will stay the same even if you just minimize the function z, okay. So adding a constant does not change the optimal solution, okay. So therefore we obtain this because we have now thrown away one of the component, okay. So now this has been simplified into this form subject to the constraints that we have here, okay. So the above program is a linear program in y as both objective function and constraints are linear in y. So these constraints anyway were linear because we are focusing on those optimization problems that have linear constraints, and the objective function is also linear, as you can see, because these partial derivative of z with respect to xi, this is known because we know the gradient of the function z at the given point xn. Xn is known at this iteration, nth iteration, okay. So the derivative of that function is also known. So only thing is not known is y, okay. So that is why this is a linear function here and these are anyway linear constraints. So this is a good news that this optimization problem to find this variable y is a linear program. So once we determine this y, this is the yn because we are at the nth iteration. So then we can determine this feasible direction yn minus xn, okay. So why it is a good news that it is a linear program, because linear program are probably the simplest optimization problems that we have encountered so far, okay, because there are many efficient algorithms, many polynomial time algorithms to solve them, and for very small problems we can just directly use this property that the optimal solution lies at one of the corner points. So note that the solution yn is the one that offers maximum local drop in the function value from xn as we use the value gradient of z at this point to find it. So if you remember when we were discussing about this point yn, we had said that we want to find that point which offers the maximum drop in the function value, but we had said local in the bracket, because when we are solving this optimization problem to find y that we saw in the previous slides, so we are using the derivative of the function z at this point xn, okay. Now this gradient information at xn may be different from the points which are near xn, okay. So that is why the actual decrease that you see from in the objective function value from xn till yn may not be just be simply the rate of change of the function value at xn times the distance that we go in the direction, because the gradient information may not be equal for all the points connecting xn to yn. So that is why this maximum drop in the function value that we see from xn to yn, that is maximal in the locus sense, it may not be the actual maximal. Okay, we think it is the maximal because we are using the information of the gradient at this point xn, but it may not be. Okay. And therefore, there may be a point between xn and yn where the lowest value of function z occurs. Okay. So, therefore, the next step of this convex combinations is to find move size alpha n between xn and yn, so that we get to that point between xn and yn where actually the objective function is the lowest. So, we want to decide that how much we want to move along in this direction. Okay. Note that all the points between xn and yn are feasible, as both xn and yn are feasible, and the feasible region is given by linear constraints. Okay. So, xn anyway is the current point that we are current. So, it has to be feasible point, and yn, when we are determining it from the optimization problem that we just discussed, so that was ensuring that this new point yn is feasible. Now, since the optimization problem that we are focusing on is having linear constraints, so the original optimization problem has linear constraints. So, if we find 2 points xn and yn which are in the feasible region, all the points in the line segment connecting xn to yn will be lying in this feasible region, because linear constraints form a convex region. Okay. And therefore, by the definition of convex region, if you pick any 2 points in this region, the points on the line segment connecting those 2 points will always be in the feasible region. Okay. So, to find the optimal move size, we solve the following line search problem. So, we want to minimize this function z here. Okay. And subject to this alpha varying from 0 to 1. Now, you can see that here we want to find that x between xn and yn where the objective function value is the least. Okay. So, to represent any general point which is lying in the line segment joining xn to yn, we return it by xn plus alpha times yn minus xn. So, you can see that when alpha is equal to 0 here, this thing will be equal to xn, and when alpha is equal to 1, this thing will be equal to yn. Okay. And if you take any alpha value which is between 0 and 1, then it will be lying between xn and yn. Okay. So, since alpha is a single variable here, this can be solved by interval reduction method. So, here when we are solving this optimization problem, xn anyway is known, yn also is anyway known by the previous optimization problem that we solved. Okay. So, the only thing that we want to determine is this variable alpha, okay, where alpha goes from 0 to 1. So, there is single variable here in this optimization problem. So, this can be solved by any of the interval reduction methods like golden section method or the bisection method that we discussed. So, after solving this, whatever alpha we get is the alpha n, because we are at the current iteration n. Okay. So, we had already determined yn by solving a linear program that we saw a few slides back, and alpha n we are determining it by this optimization problem. So, we can now put alpha n and yn in this equation here, and we will be getting x n plus 1. Okay. So, x n plus 1 is a convex combination of x n and yn. So, you can see here is that whatever x n plus 1 you get is a convex combination of x n and yn, or a weighted average of x n and yn, because it is written in this form. Because if you take the terms which are having x n in common, what it is saying, it is 1 minus alpha n times x n plus alpha n yn. I mean, this is what it is. Okay. Where alpha will be lying, alpha n will be lying between 0 and 1. Okay. So this is a kind of a weighted average of xn and yn, that will give us xn plus 1. Okay. So that is why this algorithm is called convex combination algorithm. So to summarize, given a current feasible solution xn at the nth iteration, the algorithm is as follows. First, we determine the direction in which we want to move. That is, we determine yn that solves, minimize this gradient z xn dot y transpose subject to these constraints. Okay. So these constraints ensure that this point y that we are trying to find is a feasible solution. Okay. So this is a linear program to find the direction find, and then is this step size determination. So here we are minimizing along the line segment joining this xn and the yn that you obtained from this step. So we want to determine that point which is connecting xn to yn, where the objective function value is the least. Okay. So that is why alpha here is lying between 0 and 1. Okay. And then once we have alpha and yn, then we can plug it in this equation here, and then we will be getting xn plus 1. Okay. Now we can have some termination criteria or a convergence test here. So if you find that the difference in the objective function values has become less than some predetermined constant kappa between the two consecutive iterations, then you can stop. That is, z xn minus z xn plus 1 has become less than or equal to kappa, then we can stop. Otherwise, what we will be doing here is that we will be setting n equal to n plus 1, and then we go back to this first step here. Okay. So this is what we are doing. So we first find the direction in which we want to go. So that is why we are determining this yn, because yn minus xn gives us the descent direction, and how much to move along in this direction is given by alpha n, and for that we do this step size determination. We solve this optimization problem. We have xn, yn and alpha n, so we determine xn plus 1 here. Okay. And if the termination criteria is met, that is, the objective function value difference between two consecutive iterations has become very low, then we stop, otherwise we repeat. Okay. So let us consider this example here. Suppose we want to minimize this function z, which is varying with two variables here, okay, x1 and x2, subject to two constraints that we have here. Now this is convex objective function, and these are linear constraints. So in order to determine this point yn, that is a descent direction, we will be determining the gradient of this objective function. Okay. Now since this gradient function will be required in every iteration that we move along, that is why let us write down the expression for this gradient. Okay. So this is very simple. So first you just take the derivative of this with respect to x1, and then with respect to x2 here. Okay. So that is what we will be getting. So therefore, now that we have the gradient information of this function, so we can now write the linear program to find the descent direction. Okay. So this is the partial derivative of this function with respect to x1 times this y1 plus the partial derivative with respect to the second variable x2 times y2, and subject to that this new point y1 comma y2 should be feasible. So that is why we have written down it in this form. Okay. So this is a linear program because x1 and x2n are known, only y1 and y2 are unknown. So this can be solved very easily, given that we know x1n and x2n at the nth iteration. So we are keeping these things ready for every iteration n. These are the general linear program at the nth iteration. Now another important step that we will be requiring is the move size, okay, that is how much to move along in this direction that we find yn minus xn. So for that, although we should ideally use interval reduction method, but since this problem is small, move size can also be determined by taking the derivative of this equal to 0. Okay, so if you do that, that is, you have the objective function z given to you, so that I had shown in the last slide. So in that, put this xn plus alpha n times yn minus xn. Okay, so then you will be getting the expression of this function z with respect to xn plus alpha times yn minus xn, and then take the derivative with respect to alpha and then equate it to 0. So this is the expression that you will be getting. So I will leave it as an exercise for you to do. Okay. Now just to remind again, so in all of these discussions, since we had started about traffic assignment, one very good reference that we have been following is this book by Joseph Sheffi on urban transportation network. So this example is also from there. So one more thing which I would like to add here, which probably is not mentioned in this example in the book, is that ideally we should also check that the second derivative of the objective function at the obtained alpha n that we got from the previous expression is positive, and the second derivative at each point in the interval that you focus is non-negative, okay, to sufficiently ensure that the obtained point is in fact the minimum. Okay, so if you recall, these were some sufficiency conditions to ensure that if you find a stationary point, then it is in fact the minimum point. But these are sufficiency conditions, so if these are not holding, then it does not imply that the point may not be minimum. But if these happen to be true, then you are definitely sure that it is the minimum point. Okay, so that is what it is saying, these are sufficiency conditions. Okay, so since this is a small example that we are discussing, that's why it is easier to just take the derivative with respect to alpha and make it to be equal to 0. But ideally you should use an interval reduction method to solve that. So while using this method of equating the derivative to 0, if alpha n lies outside the interval 0 comma 1, then one should use one of the interval reduction methods. Okay, so ideally one should use interval reduction method to solve the problem in the move size, because it is involving one variable. But in this example we can also just equate derivative equal to be 0, but we need to be careful. Okay, doing this derivative equal to 0, if we find alpha n lies outside the interval 0 comma 1, then we should use one of the interval reduction methods. And in order to be sure that this point that we are finding is in fact the minimum point, we should also ideally check these conditions also. Although if these conditions are not satisfied, that it does not imply that the point will not be a minimum. Okay, so let us start with an initial point. Suppose you start from 0 comma 0. Okay, so then the gradient of the objective function at this point is 0 comma minus 10. Okay, so you can put this value and you can check, and with this the linear program to find the variable y is given as this. Okay, so there was one more term here, but it was 0 times y1, so that's why there is relevant term is just minus 10 times y2, subject to these constraints here. So the solution of this can be found by inspection, because this is a small linear program, so the solution lies at one of the corners. So when you do that, you will be finding that there are two candidates for the optimum solution, either 0 comma 6 or 4 comma 6. In this case you can pick any one of them. Okay, suppose without loss of generality, let us choose 4 comma 6 here. Okay, so this is the point y. So this one will give you the direction in which you want to go, but still you want to decide how much you want to go. For that you need alpha. Okay, now we had already determined the expression for finding alpha n by taking the derivative of the function z with respect to alpha and equating it to 0. So we have already had that expression, and now we just need to put values in that. Okay, so we can put the values and we will get this alpha 1 equal to 0.75. Okay, so we have determined alpha 1, we have determined y1, so we can then determine these new points x12 and x22 for the next iteration. So this is x11 and this is x21. Okay, and this is the alpha, and these are the points y1 y2 that you got, and this was the initial point that you were currently 0 comma 0. These are the 2 points that we get here. Okay, now we can determine the objective function at this new point 3 comma 4.5. It comes out to be minus 22.5. Okay, now when we determine the difference of the objective function that we get, it is 22.5. This is still larger than the minimum requirement that we have of the threshold 0.1. So therefore, we cannot stop here, and we will proceed to the second iteration by going to step 1 with x2 equal to 3 comma 4.5. Okay. So this is the diagram which is showing this progression of the algorithm in this example. So we start with 0 comma 0 here, and then we reached this point here. Okay, 3 comma 4.5, and if you continue in further iterations, you will be getting these points here. Okay, and finally the optimal solution is here. Okay, so if you do enough iterations, you will be reaching here 4 comma 4.5, and the objective function value is this at this point. Also, if we didn't have constraints in this optimization problem, the optimal point would have been this 5 comma 5. Okay, so at this point the objective function value would be minus 25. Okay, and you can see that the objective function value when there are constraints is lesser than when there are no constraints. This is not surprising, because when there are no constraints and you are doing minimization, so then the objective function value can only be lesser or stay the same as compared to when there are constraints. Okay. Okay, so with this example we will be ending this part here, and we will be continuing in the next lecture. Thank you.